Okay, lesson 9 on page 39.
So we're doing lesson no?
Lesson 9. What's nil mean?
9
In what?
German.
Is it?
No, 9 in German is no.
Or does that mean no?
9 in German is no, but 9 is like net or something. I don't know. I'd have to ask my mom. She was a German teacher.
Okay, so a sequence is a list of numbers written in a definite order. Back in 20-1, you guys learned about sequences and series. The terms of a sequence can be found by using the general term formula. And so again, this is something that you did learn in 20-1.
Brings me back.
Yes, if you want to find the first 5 terms of the sequence defined by T sub n equals n over n squared plus 1. So if you want to find T sub 1 or term 1, you're going to let n equal 1 in this expression. So it'll be 1/2. Term 2, T sub 2 will be when n is 2. So that'll be 2/5. Term 3 will be when n is 3. That'll be 3 over 10. Term 4 when n is 4. And term 5 when n is 5. So if we write out these 5 terms, and it would keep going. And there is a pattern here. The top number is increasing by 1 as you go from term to term. The difference in consecutive bottom numbers has a pattern as well. So to go from the first denominator 2 to the second 5, you go up by 3. And then you go up by 5. And then you go up by 7. Then you go up by 9. So it's increasing always, and it's increasing at a rate of 2 more than the previous time. So there is a pattern there as well. Now we can draw a graph of this sequence, and you would see that as n increases, T sub n decreases and approaches 0. And there is no restriction on n. It goes on to infinity. So then we could say the limit as n approaches infinity. This is the first time we've seen this, where n is approaching infinity. Before, n always approached some number. Usually that was a non-permissive value, but this is different. Now n is approaching infinity. But in this case here, the pattern of these fractions is that they are getting smaller and smaller and smaller, so they will approach 0. The calculator doesn't want to wake up. Try again. Okay. So an infinite sequence is said to be convergent if it has a limit. So again, these values of these fractions will approach 0. They get closer and closer to 0. I was going to put those decimals in the calculator, but again, it doesn't appear to want to wake up yet. Okay. So we're asked to find the value of these limits. As n gets bigger and bigger and bigger, what's happening to 2n plus 1 over n? So we can do the same thing as we did on the previous one. The first term will be when n is 1. 2 times 1 is 2, plus 1 is 3, over 1 is 3. Term 2 will be when n is 2. 2 times 2 is 4, plus 1 is 5. 5 over 2, or 2.5. Term 3, when n is 3. So on top, 2 times 3 is 6, plus 1 is 7 over 3, which is 2 and 2/3. Or 2 and 1/3, I'm sorry. And we don't always have to go up by ones. We could skip a bunch of terms and find the 10th term, for example. when n is 10. That'll be 21 over 10, which is 2.1. So the values of the expression, as n gets larger and larger, it went from 3 down to 2.5, down to 2 1/3, down to 2.1. If we found, let's say, term 50, it would be 101 over 50, and 101 over 50 is 2.02 exactly. So I think that we can guesstimate in this case that this limit would be positive 2. As n, the term number, gets larger and larger, the value of the expression appears to be approaching a value of positive 2. So that we would say would be the value of that limit. Looking at question B, we want to find the limit as n approaches infinity of 2n plus 2. So in this case here, there is no denominator. The first term will be when n is 1, which will be 4. The second term when n is 2, which will be 6. The third term when n is 3, which is 8. So there's a pattern here that the value of the expression is increasing at a constant rate of 2, it would appear. If we skip some terms and find the 10th term, that'll be 22. If we find the 50th term, that'll be 102. And I think it's fairly obvious that as n gets larger and larger, the expression will just get bigger and bigger. And so in this case here, we would say that it would approach positive infinity. But it's not really approaching a value because the value of the expression is going up at a constant rate. So on the previous one, it got closer and closer to a specific value. In this case, that's not going to happen. It's just going to keep getting bigger and bigger and bigger. So it's not like it's approaching a value like the previous one. And so in this case here, we would say that this limit is divergent because the value of the expression is increasing at a constant rate. The difference between successive terms is always the same. So in this case, and I'm going to erase it, it's actually not going to approach infinity. In this case, the limit would not exist because it's not approaching a specific value. The value of the term just keeps rising at a constant rate. The difference between successive terms is constant, not like the last example, where the difference from one term to the next was always decreasing, which is why we can say that it is approaching a certain value. So again, this sequence is divergent because the limit does not exist. Whereas the previous one would be convergent. Okay, looking at this next one. We want to find the value of this limit. So term 1 would be negative 1 plus 3 over 1. I'm sorry, that's not right. It's 1 over 3n. Fix that. So that'll be negative 1 plus 1/3 or negative 2/3. That's term 1. Term 2, when n is 2, would be negative 1 plus 1/6 So that negative 1 we would say would be negative 6 on 6 plus 1 on 6 would be negative 5 on 6. If we found the fifth term, negative 1 plus 1 over 3 times 5. So that's negative 1 plus 1/15. Negative 1 would be negative 15 on 15 plus 1 would be negative 14 on 15. If I found the 20th term, let's say, it would be negative 1 plus 1 over 60. The negative 1 we'd write as negative 60 over 60 plus 1 is negative 59 over 60. So I think we can see from this pattern that the values of the term are approaching negative 1. We're getting closer and closer to negative 1. The difference between successive terms is not the same. That gap is always going to get smaller and smaller. So it is approaching a specific value, and we would say that that value is negative 1. Okay, so this is one way to evaluate these limits as the variable approaches infinity. But now we're going to see an algebraic way that we can do this, and then we'll talk about some observations that we can make to make it a little bit easier as well. So this is in your textbook, these properties of limits. So if the limit as x approaches a of f at x, and if we have the limit as x approaches a of g at x, then the limit as x approaches a of f at x plus g at x can be found by taking the sum of the individual limits. The limit as x approaches a of f at x plus the limit as x approaches a of g at x. Same thing if you have the limit of the difference of the two functions. It is the same as the difference of the limits of the individual functions. When you have a constant, this is what number 3 is saying. The limit as x approaches a of c times f at x. C is a constant. There is no x there, so it doesn't matter what happens to x, that c part will not change. So because of that, you can bring the c in front as a coefficient of the limit, like number 3 shows. And then just like for sum and difference, the same rules work for product and quotient of a limit. The limit as x approaches a of f at x times g at x is the same as the product of the individual limits. Same thing with quotients. Okay. And then number 6 says the limit as x approaches a of some function f at x to the power n. Well, that can be the same as the individual limit as x approaches a of f at x to that whole thing to the power n. So you see the patterns here, right? There's basically, we're kind of using the distributive property in these cases. Same thing with the root one. So we can use these properties of limits to help us evaluate limits. Yes, you get those properties on a formula sheet. You don't have to memorize them. Okay, so this is a method that you can use to evaluate a limit as an algebraic approach instead of doing that guess and check method where you're changing the values of n and then kind of guessing what the limit will be. What I'm going to show you now is an algebraic approach to evaluate limits, and then we'll make some conclusions after we go through a few of these that we can use for future questions. So we're going to break each of these up using what we know about the property of limits. The other thing we're going to do, as we break them apart, we're also going to divide each term by the highest power of the variable. So if we look at this first expression, you've got the limit as n approaches infinity of n squared plus 3n all over n plus 1. The highest power on n there is the n squared. So I'm going to do two things here. I'm going to use the property limits to break these up, and also I'm going to divide each term by the highest power of n, which is n squared. So this is what it'll look like. It'll be the limit as n approaches infinity of n squared over n squared plus the limit as n approaches infinity of 3n over n squared all over the limit as n approaches infinity of n over n squared plus the limit as n approaches infinity of 1 over n squared. Again, I did two things there. I used those properties of limits to break it all apart, but at the same time, I also divided all of the terms by the highest power of n, which is n squared. So we can do some simplifying here. That first term will just be the limit as n approaches infinity of 1. The next one, I can divide top and bottom by n, so that'll become the limit as n approaches infinity of 3 over n. The next one, I'll divide top and bottom by n again, and it'll become the limit as n approaches infinity of 1 over n. And the last one, I can't simplify at all, so it just stays the limit as n approaches infinity of 1 over n squared. So we can now evaluate each of these limits. Okay, so if we look at the first expression here, this one that I've just underlined, it doesn't matter what n does, because that term has been simplified just to be the limit as n approaches infinity of 1. There is no n there. So it doesn't matter what n is, that first term will be 1. Okay? Now the second term on top, the limit as n approaches infinity of 3 over n. So that means that n is going to get larger and larger. N as approaches infinity. And when you divide 3 by a number that gets bigger and bigger, your answer will get smaller and smaller. For example, when n is 1, you'll get 3 over 1. When n is 2, you'll get 3 over 2, which is 1.5. When n is 10, you'll get 3 over 10, which is 0.3. When n is 100, you'll get 3 over 100, which is 0.03. As n gets really, really big, 3 divided by a number that gets bigger and bigger will get smaller and smaller. It will approach a value of 0. That's the value of that second limit on top. Same thing's going to happen for that first term on the bottom, right? You've got the limit as n approaches infinity of 1 over n. As n gets bigger and bigger, 1 over n will get smaller and smaller. It will approach a value of 0. And the same thing with the second term on the bottom. It's going to approach 0 faster than the first term on the bottom, because whatever value of n you have on the bottom, it's going to be squared. So the denominator is going to get bigger faster, and 1 divided by a number that keeps getting bigger and bigger will get smaller and smaller. It'll approach a value of 0. So this will be 1 over 0, which does not exist. That is the value of this limit. It does not exist. And if we look at the original expression, and I talked about drawing some conclusions that we can use for future types of questions. If we look at the original expression, the degree of the top is degree 2, the degree of the bottom is degree 1. Whenever the degree of the top is 1 more than the degree of the bottom, this will always happen. You're always going to get a 0 plus 0 or zeros on the bottom. And so whenever the degree of the top is 1 more than the bottom, the limit as n approaches infinity of that expression will always be that it doesn't exist. So you can remember that. And it saves you from doing this process over again, if you remember that. Okay? Now, the difference between that question D and E is that with E, the degree of the top and bottom are the same. They're both n squareds. So let's see what we get when we evaluate this limit. We'll do the same thing. We'll break it up into individual limits, and at the same time, we'll divide top and bottom by the highest power of the variable, which is n squared. So the second term on top will be n over n squared. On the bottom, we'll have the limit as n approaches infinity of 2n squared over n squared, plus the limit as n approaches infinity of 1 over n squared. So I broke it up using the properties of limits, and also I divided each term by the highest power of n, which is n squared. And like before, we can do some simplifying. So that first term on top, the n squareds cancel, that just becomes 1. Second term on top, you divide top and bottom by a factor of n, and that becomes 1 over n. First term on the bottom, the n squareds cancel, and you're just going to get the limit as n approaches infinity of 2. And for that last term on the bottom, there's nothing we can do to simplify. So now we'll go to stating the value of this limit. So the first term on top, the limit as n approaches infinity of just 1. There is no n left there anymore. So it doesn't matter what n is, that first term will always be 1. It doesn't matter what happens to n. But for the second term on top, the limit as n approaches infinity of 1 over n. Again, n is approaching infinity. It's getting larger and larger. 1 divided by a number that gets bigger and bigger. That quotient will get smaller and smaller. It will approach 0. On the bottom, that first term is going to just be 2. There is no n left after you cancel the n squareds. It doesn't matter what happens to n. The value of that limit will not change. It'll be 2. Plus, on the bottom, that second term, the limit as n approaches infinity of 1 over n squared, that will be 0. As n gets larger and larger, n squared will even get bigger and bigger, but 1 divided by a number that gets bigger and bigger, that answer will get smaller and smaller. It'll approach a value of 0. So 1 minus 0 over 2 plus 0 is 1 over 2. So in this case, the degree of top and bottom were the same. And if you look at the coefficients of the n squareds in the expression, the coefficient of the n squared on top is 1. The coefficient of the n squared on the bottom is 2. 1 divided by 2 is 1/2. That is the value of the limit. You can use this. If the degree of the top and bottom are the same, then the limit as n approaches infinity will be the coefficients of the highest power terms divided. Okay, and we did talk, or you probably did learn a little bit about this in 30-1 when you were graphing rational functions, and rational functions had a horizontal asymptote, and this is how we found out where that horizontal asymptote was. We actually found, without talking about limits, we were finding the limit as n approaches infinity of that expression. And if the degree in top and bottom were the same, it was always those coefficients that gave you the horizontal asymptote when you graphed rational functions. We were really finding the limit as n approaches infinity when we did that, without talking about limits. Okay, so that's a rule that you can use now. Remember, if the degree of the top is 1 more than the bottom, then the limit does not exist. If the degree in top and bottom are the same, you can find the limit by just dividing those coefficients of those highest power terms. So now we can say the same thing for question E. The degree of top and bottom are the same. They're both x squareds. So we don't have to go through all that work of breaking them up and dividing each term by x squared. We can just say the limit is the coefficients of the x squared terms, which is a 1 on top over a 4 on the bottom. That's the value of that limit, 1/4. Same thing with question F. The top expression is a third degree polynomial, and so is the bottom. So the limit as x approaches infinity of that expression can just be found by dividing those coefficients of those highest power terms, which would be 2 over 6 or 1/3. You don't have to break them up and do that work that we did on the first two. But in some cases, you have no choice, but you have to use that table of values method, the guess and check method if you want. Okay. So in this case here, if we find the first term, it'll be negative 1 to the power 1, which is negative 1. If we find the second term, negative 1 all squared is positive 1. If we find the third term, it'll be negative 1 to the power 3, which is back to negative 1. The fourth term would be negative 1 to the power 4, which is back to positive 1. I think you can see that when n is an odd number, you're going to get an answer of negative 1. When n is an even number, you're always going to get an answer of positive 1. These terms will just keep going back and forth between negative 1 and positive 1. The difference between each term is not changing. So in that case, this limit does not exist. It's not approaching a certain value. And we cannot use the tricks that we've just learned about because this isn't a rational function. Right? So that's what makes it different. Now, this next one is a rational function, sure, but again, the difference is that the exponent is the variable. It's not like the ones that we saw on the previous page where the exponents were whole numbers. So we could use those rules that we've identified. Again, this one is different. The exponent in this case is the variable. So once again, we would do this basically by some guess and check. The first term will be 1/2 to the power 1, which is a half. The second term, 1/2 all squared, is a quarter. The third term, 1/2 all cubed, is an eighth. So it appears that the values are getting closer and closer to 0. Let's find the 10th term. 1/2 to the power 10, I think, is 1 over, is that 1,024? 2 to the 10th? Yep. So again, the denominator is getting larger and larger. When you divide 1 by a number that's getting bigger and bigger, the answers will get smaller and smaller. They will approach the value of 0. Okay, so again, sometimes you have to use this method to evaluate the limit. Same thing with question L. The variable is the exponent. N is going to approach infinity, so negative 1/3 to the power 1 is negative 1/3. When n is 2, you're going to have negative 1/3 to the power 2, which is positive 1/9. When n is 3, you're going to have negative 1/3 to the power 3, which is negative 1 over 27. So in this case here, it's going from a positive to a negative to a positive, depending on whether n is even or odd. So that'll be positive 1 over 81. In this case, there is a limit. It doesn't matter that the values of the term are changing from negative to positive and then back to negative again. These numbers are approaching 0. And you could see that if you drew a simple graph of this. Now we're going to have to change our scale here, or have a scale of 1 on this. So when n is 1, you're going to have negative 1/3. Let me change the color for the graph, which is approximately right there. When n is 2, you're going to have positive 1/9, which is 0.1 repeating. So that's closer to the x-axis than the previous point. Sure, it's on the other side of the x-axis, but it's still closer. The third term, you'll have negative 1 over 27. So that's negative, but again, it's closer to the x-axis than the previous point was. Yeah. A positive and a negative and keep going back and forth? Not necessarily. You'd only say that the limit doesn't exist if the difference between successive terms is not changing. In this case, the difference between one term to the next is changing. And the graph shows us that. It depends. Each one is different. You have to look at each one separately. Okay, so the fourth term, it's positive 1 over 81. So again, in this case, it's above the x-axis. But you can see that each point is getting closer and closer to 0. In this case, the limit does exist. The limit is 0. All right? So again, you have to remember these rules now. Well, you don't have to. You can, if you want, you can go through all the work that we did to develop those rules. But if the degree of the top is 1 more than the bottom, then the limit does not exist. If the degrees are the same, then you can just divide the coefficients. Now, the only one that we didn't do in these questions is what about when the degree of the top is 1 less than the bottom? And when that happens, it will approach a value of 0. Okay, back in 30-1, when we graphed the rational functions, we saw that when the degree of the top was 1 less than the bottom, then the x-axis was an asymptote. And so the value of that limit was 0. And if we go back now to some of the ones that we did using the properties of, or using our guess and check method, see, there's one where the degree of the top is less than the bottom. And we saw that it was approaching a value of 0. In this case here, we did it by guess and check. For question A, the degree of top and bottom were the same. So if you just divided the coefficients, 2 over 1, which is 2, you would have got that limit. And so these tricks, if you want, can only be used if you have a rational function. Now, you could have done that for question C. We just would have to combine those two terms to make it a complete rational function. So what it would look like the limit as n approaches infinity. Negative 1, we need to write that with a denominator of 3n so we can combine it with the second term. So negative 1 would be negative 3n over 3n plus 1 over 3n. So now we can combine those two and say this is the limit as n approaches infinity of negative 3n plus 1 all over 3n. The degree of top and bottom are the same. The coefficients would be negative 3 divided by 3, which is negative 1. That's the value of that limit. Because the degree of top and bottom are the same, when you combine them, you can just divide the coefficients to get the limit. You don't have to use that guess and check method. Okay, so remember those rules. It'll make evaluating these limits much easier. One of the things that we will use this for when we get into curve sketching, we're going to learn how to sketch pretty much any function, any equation you want using calculus. Okay, and one of the things we will talk about is what is the limit as the variable approaches infinity. This tells you what the behavior of the graph will be when it goes to the right forever or to the left forever. That's the limit as the variable approaches either positive or negative infinity. Okay, so we'll apply that when it comes time to sketching curves. So what you should work on is page 50 to 51, numbers 3 through 5. I will post those answers on Google Classroom for you. Tomorrow we have one last lesson. We'll also go through that limits quiz that you guys wrote so you can see what your mistakes were. And remember, on Thursday is your exam. I will also hand out today your review assignment, so if you want to start working on that, you can. That will be due for marks. It'll be due on the day of your test, which is Thursday. Okay?